we're going to, we're going to continue in 12.1. We're solving systems of linear equations, right? I had shown you one method, which I called substitution, right? Yes. And now I'm going to look at a separate method called elimination. And you're always free to use either one. Elimination's more powerful from when we have more variables and more equations. Yes, exactly. Very good. So let's look at a problem. Let's go with 3x minus y equals 7. And the other one, 9x minus 3y equals 21. Now this is kind of picking up exactly where I left off last class. If you remember the last example I did, we got something really weird at the end of the problem. And we determined that the lines didn't intersect each other, that they were parallel lines. So let's take a look here. Going off of what we did last class, what would you choose to do at this point? Solve for y in the first equation, right? It's probably the easiest thing to do. So taking the first equation, 3x minus 7 equals y. So I just move the y to the right, move the 7 over. Is that okay? And now we go to the second equation and we replace that y with this. So here's the second equation. And we replace the y with what? 3x minus 7. We make sure it's in parentheses. And then equals 21. 9x minus 9x plus 21 equals 21, right?
So we have 0x equals 0.
So we get 21 equals 21, which you could say is 0 equals 0 if you subtract 21 from each side. But the point is that that statement is always true, right?
Yeah.
Last class, last problem I gave you, it was like two numbers that said were equal, which weren't. And we said, well, that corresponds to two lines being parallel. What's happening here?
Inverse?
Not quite. Think about what are the possibilities if somebody gives you two lines sitting on a flat sheet of paper. Yes, exactly. What we did before, not the last problem from last class, but the problems before that, we were finding the point where they intersected, right? Then the last problem we did, we realized, well, you know what? They're parallel lines. They don't hit each other at all. And here we're getting a statement where we're not going to be able to solve for x or y. And we're just getting that it's always true, which means that they are the same line, right on top of one another. So whatever's going to make this equation true is actually going to make that one true. Every x and every y that you pick here will also satisfy this one. So let me see if I can come up with a quick example. If I use 3 and 2, right? 3 here would give me 9, minus 2 would give me 7. Make sense?
Yeah.
But if I do that here, it's going to work also. 3 times 9, 27, minus 3 times, what, 2? 6, is that 21?
Yeah.
Yes. And it turns out that if I continue to find more and more points, every one of them is going to work in both. So it's the same line. So the big question is, well, how do you answer the question then, right? It's asking to find the solution. There's an infinite number of them. But keep in mind, we're saying there's an infinite number of answers, right? Let me give you another answer that works, just so we can see this. How about 0 and negative 7? Will that work?
Should.
0 here, negative 7 is positive 7, that works. 0 here, negative 3 times negative 7 is 21. So that works. Am I saying that every point I ever pick will work? Like if I just pick 5, 4, that doesn't work in the first one, right?
But that's because it's not the part of the line.
That's right. So we can't say there are an infinite number of answers, but it's not just any number, right? It's got to have a special property. So the way we write this is as follows. It's going to be the set of all points. You know, normally we would write the answer here like 5, 4, if that were the answer. If we get parallel lines, we say no solution, right? No solution. But if it's this case, what we do is we write x, and then over here, 3x minus 7. Now, what did I do there? What am I saying?
They're one and the same, isn't
This is this line, right? I'm saying that if you pick an x coordinate, right, I guarantee you that the y coordinate, right, has to lay on the line, which means it has to follow the equation, right? And you can check my 3 and my 2. Does it work here? 3 and 2 worked. 0, negative 7. 0 here, 0 here, kills it off, negative 7. Can someone quickly give me what would another point be? Use this.
So if x was 1,
Then y would be
3 minus 7, which is negative.
good. How about if x was negative 2? Negative 13. You see that? You can use this formula to generate all the different answers. But since there's an infinite number of them, I can't list them all out, so I just give you a formula.
Right, because you can't say all real numbers. It's not.
Yeah. All right, so just a quick recap. If you're trying to solve a system of linear equations where you have 2 variables and 2 unknowns, there's 3 possibilities. You can have one solution, a point where they hit each other. You can have no solutions. We call that an inconsistent system. That's where the 2 lines are parallel. That happens when you work through the problem and you get some ridiculous statement that says something like 4 is equal to 0. That's how you know. Then you can have 2 lines, but they're actually the same line right on top of each other. That you would know because you work through and you get something like 21 equals 21, which is always true. In that event that you get that it's the same line, you just go to that first equation you solved, put x here, and then put whatever you solve for y, just put it here. Just always put x here, and then put that y right there. That's your answer.
Seems kind of simple.
That's it. Okay? Now I'm going to change the problem.
I can foresee this being kind of confusing but more complicated.
Yeah, once we get to 3 equations and 3 variables, it gets a little more confusing. Let me change the problem. I want to do the same thing, but this time I just want to use something like negative 6. So these are definitely not going to be the same lines anymore. All right, we know how to do this with substitution. We would go through the same story, right? Solve the first equation for y, replace it in the second equation, and solve, right? Do you want me to show you that, or can I move on to the new method today? New method? All right, so the new method, which is called elimination, I said was more powerful. And here's how it works. I could write the steps out, but it's confusing. I think once you see it, I think you'll kind of catch on to it, and then you'll be like, all right, I know what to do. So I look at my system of equations. I make sure that my x's are lined up, my y's are lined up, and my numbers are lined up. Okay, just make sure everything's in order. And then look down as almost like this is a column. These are your x's, these are your y's, these are your numbers. Look at the x's and think about what it would take so that if I added these 2 together, the x's would go away. So for like right now, if I add this to this, I will get what, 12x? I want to be able to add them together and get 0 x's. I would have to multiply the top one by negative 3, right? Since this is an equation, you can always do the same thing to both sides, and it's still the same equation. So what I can do is just tell myself what I'm about to do. I'm about to multiply this top equation by the number 2. I'm just going to put it out there in red like that so you know what I'm doing. And now I'm going to rewrite the entire system with that 2 passed through the entire equation, both sides. Yeah, I don't know why I put that 2.
I was like, that'd be 6.
I have no idea why I put that 2.
You're testing.
Yes, thank you for paying attention. I would have found out right in the next step when I distributed it through. I would have known. Now, hold on. Is this going to work? We're still off a little bit. If this is 9, 9x plus 9x is?
0x.
Nope. 18. So it needs to be negative 3. Aha, so two little things there, right?
Got 'em.
I'm not sharp today. Something's going on. I had some problems in my Cal 2 class today also. Okay, negative 9x is what you get when you go here to here. Now here to here,
Negative. No, positive 3y.
positive 3y. And then you also must distribute over here because it's really like you're multiplying both sides. So negative 21. And then the second equation, I'm not going to touch it. I'm just going to leave it alone. Now what we will do is exactly what kind of influenced us to do this, and that's we're going to add these two equations straight down. So when you add down, what do you get here? 0, which is what we wanted. And then we get here? 0. Crap, this is not what I wanted to happen. 0 equals, you know what, I really want this to work. Can I just change one little thing?
Change the line.
I'm just going to change this to a plus. Can you all change that to a plus to start the problem?
Okay.
And then change that to a plus. Now when we add straight down, what happens? 6y. And I'm going to do this over here because it's below this. I'm not writing a new system. This is 6y equals negative 27. Understand?
And then just solve for y.
Now look, what we have is an equation that just has y in it. We have eliminated x, haven't we? That's where it gets its name from.
Oh, and
All right.
then you would do it for y.
You don't have to do it for y because as soon as we know what y is, we can go back to any equation, plug in the y value, and get x. Right? So, but it's going to be a fraction. That kind of sucks, but you know that's life. Sometimes that happens. So we know what y is. I can box it, and now I do what we call the back substitution. That's what this step is called. Back substitution. The only reason I tell students that it's not really in the book that it's called back substitution. I just like to abbreviate it as BS, and then I can say this is the BS step. You know? No, it is technically called back substitution. So I'm going to take that answer, I'm going to back substitute it back into any of these. You're free to work with any equation you want. I always prefer to go to an equation that the original one, because I know that it's not messed up. Like, you know what I'm saying? I could have made a mistake in here, but up here those should be legitimate equations. So I'm going to go to the first one. 3x minus y equals 7. I'm going to replace my y with what? Negative 27 over 6.
You can kind of round it off to like negative 9.5 or something like that.
Negative 9. Oh, reduce the fraction.
Yeah.
Yeah, you could reduce that fraction. Stephen is saying 3 goes into both, right? We could, if you want to work with smaller. Do y'all want to work with a smaller one or stick with this? Doesn't matter, right? Okay. So now we go to solving this. 3x plus 27 over 6 equals 7. Subtract 27 over 6 from both sides. You'll have to get a common denominator, right? Which is what? 42 over 6 minus 27 over 6. I just looked at 7 as being 7 over 1, multiply top and bottom by 6. So what is that?
Once you take it all out, it's like 23.6.
This over
Actually,
here?
I divided it all out. I just divided it out and got x.
Okay, I'm going to do that in the next step. I'm going to subtract these first. So subtract across the top. 42 minus 27. 15? 15 sixths. And then final step here. Divide by 3 on both sides, or multiply by 1/3, whatever works in your head better. In either event, you're going to get 15 over 6 times 3 is 18. And then we can reduce that answer. 3 goes into each of those. 3 goes into each of those, right? 5/6. So our answer is a point, right? We can look at it as like an ordered pair, an x and a y coordinate. It's 5/6, negative 27/6. Was that right? Okay. And yeah, you could reduce. Well, you could reduce that one.
By 3.
Yes, negative 9/2. What do y'all think of that method?
I can see why it's a more powerful method.
Yeah, I mean, they're equal in the sense that they get you to the same place, all right? But a lot of people like the substitution because they're taught that and they're used to it. So
See, there's more that could go wrong with it.
possibly, yeah. I'd agree with that statement. All right, let's look at another one. How about this? I think I'm going to make one up because I want something special to happen here.
Special. When he says something special, it ends up taking us almost 40 minutes.
All right, let's solve this system of equations.
You want to solve ourselves?
No, let's work through this one, okay? I'm going to do elimination, okay, because that's what I'm trying to get us used to right now. If you try to do substitution, you wouldn't really have a good choice of which equation to solve for, right? In terms of like the first equation for x or y, because they both have numbers in front of them, right? So eventually you're going to have to divide through by that. So like, you know what I'm saying? Like none of these are just y by itself or just x by itself. So substitution would probably not be fun to begin with. All right, so let's look at the x's. Is there something you can multiply by to get these to cancel?
Multiply 2 by 5 and then 5 by 2.
Oh, so you want me to do this one up here by 5 and this one by 2? Or one of them needs to be negative, right?
Yeah, one of them needs to be negative.
You could do that,
We don't know
absolutely.
what that's going to be to get to -5 for that x. Or the top one's equal to 2.
No, what's being suggested is that we multiply this top one by 5 to make that a 10x, and then multiply this one by -2 to make that a negative 10x.
So we also got to take into account of how it's going to affect the 3 and the 4?
Nope, you don't have to look at that at all.
Okay.
Because all we're focusing on is eliminating the x's. All right? But you can focus on eliminating the y's instead. With elimination, you do not have to do x's. You can do the y's. If I wanted the y's to cancel, what would I multiply the top by? 4, and that would make that a 12y. And then I multiply the bottom by 3, because of the negative, that would be negative 12y. Understand?
What I was actually talking about, you
Oh.
were talking about like a positive and a negative.
Uh-huh.
Like let's say we did the the top by a negative, and it got to the y's to where,
Are you saying back to killing the x's off?
yeah.
Like if I did that, that would still work. You don't care how it's going to affect these. Okay? Don't even worry about it. So let me start back here from scratch. If we're going to do elimination, you have some freedom to choose which variable you want to kill off. Because if I kill off the x's, what will remain will just be y's, right? If I kill off the y's, then what will remain should just be x's. In either case, I'm going to be able to solve for one of the variables. Understand your choice here? All right, so you want to stick to the original? 5 on top, -2 on the bottom? Okay. Okay, well, you know what? I encourage you to do that yourself on your paper and see. I bet you will get the same result. You did it already? Okay, so let's see if yours matches ours. All right, so I'm going to multiply through by positive 5 on top first, get 10x plus 15y equals 50. Multiply through by -2 on the bottom. I get negative 10x. I get positive 8y. I get positive 4. Everybody agree? Okay, add straight down. 23 y's are all I have left over, right? Equals 54. And then make a fraction out of this. Y is 54/23. And that I do not believe reduces. So now we go back and get x. Pardon?
23 prime.
Yes, but just because one of them is prime doesn't mean it doesn't reduce. They have to be, oh my gosh. I'm embarrassed that I don't know the name of this. Oh my gosh. I shouldn't, I'm embarrassed to be on camera right now. Holy shit. Yeah, I had about it's relatively prime, meaning that, look, I can give you an example of something that would reduce that one of the numbers is prime. 3 is prime, right?
Yeah.
But 3 goes into 18 6 times.
Yeah.
I don't know. 3 over 15. I don't know. I thought you were saying that this won't reduce guaranteed because 23 is prime.
No.
Okay, I thought that's what you were implying.
No.
All right, you said 23 was prime, so I wasn't quite sure where you were going with that. All right. All right, get x.
Plug it into 2x.
You want to go to the first one? Fine with me? So 2x plus 3 times 54 over 23 equals 10. It's just going to be ugly numbers, but we should be able to do this. 2x plus the 3 is like 3 over 1. You multiply. So what is that? What's 3 times 54? 162 over 23 equals 10. Then subtract on both sides the 162 over 23. What now?
We got kind of
Common denominator of 23.
So 230 minus
Yeah, 10 over 1, so this will be 230 over 23 minus 162 over 23, which is 68.
68. Oh, I did
68 over 23.
calculated broken.
2x equals 68 over 23, which means x equals 68. I'm going to divide both sides by 2 over 46, and that reduces a little bit. Two goes in both those?
Yeah.
I'm not really caring too much if you reduce, but there's your x. So it's an ordered pair again, right? The x coordinate is this. The y coordinate is this.
So you will take off any points for fractions?
No, I won't take off if you don't reduce, but you know, if you can, try to.
1,000 over 500.
I mean, it's the same number, right? Yeah.
Would you care if we like?
You know what?
Don't do decimals though. Keep them as fractions. As soon as you go to a decimal, you're basically going to have some error because you're going to round it somewhere. And I want these to be exact answers. And I want to see the algebra because this is all good practice. All right. Let's do a word problem. I like doing the chemistry mixture problems because people usually enjoy those. And in the spirit of fiesta, let's do an alcohol mixture problem.
There we go.
Okay, so this is your word problem.
Is it tequila?
Sure, we have tequila. Okay, we have
How many shots does it take till it's full?
we have 2 types of tequila. TEQU.
It doesn't.
No, yeah, it's spelled weird. You know how to spell that. You're a bartender. There you go. All right, so we have 2 types of tequila, and let's say we have like an infinite supply of this. All right, we got all these bottles of tequila, 2 different brands, 2 different types. One is, okay, do you know what the alcohol percentage on tequila is about? No? I have no idea. I forget. I don't think. Okay, let's go with 85. 1 is 85% alcohol. That doesn't run. How do you spell alcohol? A-L-C-O-H. That doesn't work. C-H-O.
I know it's C-H. It's okay, we're math. We don't
Yeah.
know about words.
Just put ALC.
A-L-C. See, I like y'all because that's what I do when I don't know how to spell something. I just abbreviate it. Of course, you know what I'm talking about.
It's got tequila, we know.
One is 85%. The other is 90%.
I want that 90.
Which one were you drunk enough to cut off your thumbs?
How much do you need to drink before you start cutting fingers off for extra credit? Yeah. All right, so let's say we have a very particular situation where the manager of this bar, the owner, does not want to serve 90% alcohol because it's too expensive, and the 85% is the cheap stuff, so he wants to make a mixture of something in between. He's going to mix the tequilas together. Right now, I'm taking this from a chemistry problem, all right, where you have like different solutions at different concentrations, but I'm making it more interesting with tequila, all right?
Are we gonna do with that?
So what we want,
I think you're gonna lose your liquor license for that.
we want a 20-liter mix of 87% tequila. So we're going to take these tequilas that we have, and remember, we have a bunch of bottles of each, so we're not going to run out of them, all right? We got a bunch of tequila, that's 85%, and a bunch that's 90, and our manager wants us to mix them together so that we get a total of 20 liters of this 87% tequila. We'll save a little money this way, okay?
And also lose your liquor license.
Yeah, I don't think you're supposed to do that, right?
I know this.
Shh. All right, so let's somehow, some way, this is a system of equations, right? The question that I have here is how much of each should be mixed? To achieve the 20 liters of 87% tequila. Is what? Tequila? You said it was two.
I thought it was 2.
It's been bothering me.
It's
sorry.
All right, we'll just abbreviate it.
Oh,
I for sure thought it was.
I speak Spanish, I know this.
Okay, so okay, since you know it, I will put it.
Bourbon.
Yeah, we should have done, vodka. Vodka is easier.
Vodka.
All right, so there we go. We've got our situation now. We need to somehow solve this, right? Your hint is that it's a system of equations, right? You want to know how much of each, right? So there's two things you want to know. How much of this tequila and how much of that tequila that you need to mix in there, right? That should probably be our variables.
Some sort of X, some sort of Y equals 20.
Well, let's see. Let's first define the variable. Let's let X be the amount of 85% tequila, right? That we're going to have. It's how much of it we need to pour in. Let's let Y be equal to the amount of 90%, right? Understand what I'm doing?
Yes.
Now, I heard already that we might be able to get one equation right off the bat.
Yes.
What do you know?
X plus Y equals 20.
X plus Y has to be 20, right? So what we're implying by this is that this is the amount of this, and this is the amount of this, and we're going to assume that we're going to measure this in liters, all right? So we're going to have so many liters of this and so many liters of this, and when we mix them together, we're going to have a total of 20 liters, right? So that's my first equation. I know that at the end of the day, when I pour the 2 into this container, that needs to be equal to 20. With me? Yes.
I was going to say the second one.
Okay, so what are you thinking on the second one?
I think 85x plus 90y equals 87 point? Or would it be? Or
This
would you
is-
have to
this is
make it into a
close.
fraction or
This is really close.
So 85 over 100.
This is, yes, you're on the right track. Let's think through it a little bit more. You're almost there. There's one critical little element missing. All right, so when we talk about a percent mixture, right? When we talk about a percent mixture, let's work with some easier numbers first, okay? What if I told you that you had to create a 50% mixture and it had to be 20 liters? 10 and 10. Is that obvious to you, right? Half and half, right? 50, oh, sorry, I shouldn't say that. No, I shouldn't say that.
No?
No, because we don't have a 50, it would be impossible for us to make a 50% mixture out of these two. Because they're both higher than 50%. Yeah, let me not distract us from this. Let me do it this way. Let's say that we have 1 liter here. All right, there's 1 liter of alcohol. And let's say that this is the 85% mixture. That means that 85% of that 1 liter is alcohol, right? And the other part is water. So if you look at it and measure it, you have 85%, so 0.85 liters is alcohol. The rest of this up here, which would be 0.15 liters, is water. Understand?
Yes.
So in order to figure out how many liters of alcohol there were in here, I would have to take this number and multiply it times this number. Give you another example. If I have 10 liters in here of 85% alcohol, how many liters are alcohol?
8.5.
8.5. How are you getting that? You're taking this and multiplying by that. So if you take 85, but you have to convert it to a decimal here. This is important, right? Take 0.85, multiply by 10, you get 8.5. If you took this as a decimal, 0.85, and multiply it times 1, you get 0.85 liters. Understand? If I have a container over here that has 20 liters, and I have the 85% concentration of alcohol in there, what would that be? Good, you go to your calculator, 0.85 times 2, how many liters? What is it? 1.7 liters would be alcohol. Does this make sense? So anytime we want to figure out how much alcohol is in the mixture, we have to take the percentage, the concentration, and multiply it times however much there is.
So it's 20.
And that's 8% of 20.
Hold on. If we do X liters at 85%, how many liters of alcohol are in here? 0.85 times X, right? That's how much would be in there. Okay, so that is where, who was saying that? You were saying you think the next equation is 85, and then you said, should we divide by 100, right? All right, so you were on the right track. Here's what we need. We need that when we take the 0.85, that's this one, right? And we multiply by how much we have, and we add that to the 0.9 concentration, 0.90, which is 90%, times Y, that's how much alcohol is coming from the 85% mixture, right? This is how much alcohol is coming from the 90% mixture. That needs to be equal to, this is a critical part, this, what? 0.87, that's the concentration,
20.
times 20, okay? 0.87 times 20. See, each one of these is the concentration times how much, plus the concentration times how much must equal the concentration times how much. Well, we know at the end when they're mixed, you have to have 20 liters, right?
Question, where did
Yes.
0.87 come?
I believe in the problem, the owner wanted to mix to get 20 liters at 87%.
I see it now.
All right. We good with this? What is 0.87 times 20?
17.4.
17.4. Okay, so I'm going to rewrite this system. This is x plus y is 20. This is 0.85x plus 0.90y must equal, you just told me, I forgot, 17.4? Okay. There's our system of equations, if we can solve it. You can use substitution or you can use elimination. It's up to you. I am going to choose to do elimination because I've only given you 2 examples. And I'm going to choose to avoid decimals by getting rid of these decimals. So how can I get rid of these decimals?
Put it over 100.
You could write them as fractions, yes, but how can you move decimals around? You multiply by 10, we'll move it to the right 1 time. Multiply by 100, we'll move it twice. I'm actually going to multiply both sides of this equation by 100, or yeah, both sides of this equation by 100 to move this over twice, this over twice. Ooh, that's going to be a big number, but that's life, okay? That's what happens sometimes. So we have x plus y is 20, and we have 85x plus 90y equals 174. 0, yes, 1,740. Elimination. Make sure you have your calculators out because these numbers are going to get big. Let's eliminate the x's. Is that okay with you, or you want to do the y's?
Do the Ys.
You want to do the y's? Someone else want to do x's? Let's take a vote. X's, show of hands. Okay, that's all we need. Okay, 85 here. You don't want to do that? You want to make it negative 85. Good. Negative 85 on the top one. Rewrite the system of equations. You have negative 85x minus 85y equals negative 85 times 20, 1,700. Rewrite the second equation, don't change it. Oh wow, I wasn't trying to make this turn out to be a nice answer, but it's actually going to turn out to be nice. 5y equals, adding straight down now, right? 5y equals 40. So y is 8. Once you know y, you back substitute, you go back to any equation, but you could actually just think through this one, right? You have, that's 8 liters, right? So you're going to have 12 to get the 20, but you could do that by just plugging in here. Everyone okay with that? Dot, 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 you could get that x is 12. So that means I'm going to take the answer to the problem is that I'm going to have 12 liters of what and 8 liters of what? 12 of the 85% and 8 liters of the 90%. If I mix those together, right, swirl it up, I'll have 20 liters of 87% mixture.
In a lawsuit.
In a lawsuit. But I'm not going to say it. That's what I was going to say. Remove all evidence. All right, so there's a few homework problems. Of course, they're not going to be tequila and things like that, but one of them is they have these this store that sells cashews and peanuts, and they charge a certain amount per pound, and they want to make a bag mixture of cashews and peanuts, and there's a question. Same sort of idea that you have to come up with these equations. There's another one. Well, I forget what the other one was. 57. Yeah, another one has to do with a restaurant manager who wants to purchase flatware for his restaurant at different costs and trying to figure out how to do it the best way. So anyway, see if you can work through the homework on your own and turn the word problem into a system of equations. Once you're there, the mechanics of this is all the same. I believe this is the way a lot of these pharmacists work with things like this. Like, they have these certain solutions. You go to like H-E-B pharmacy, they have certain concentrations of certain things, and then the doctor says, hey, I want this person to be taking, whatever, 6% of this stuff. Well, they don't go in the back and have a 6% bottle. They have to actually take their 10% and their 2% and mix it to get the 6% solution. So they make it, but they just have standard bottles in the back, if that makes sense.
When are we gonna do 3 variables?
Yeah, I think it's time. This was, yeah, right now. Okay, you ready? We're going to move on to the next thing, which is systems of 3 equations, 3 variables. Three equations, 3 variables.
Is this still 12-1?
Yeah, this is still 12.1. Yep. 12.1 is kind of a long section. I'm sorry? 12.1 still. Yep. We're still in it, and we're about halfway through it. All right, so here's what I'm going to do. I'm going to start off by putting a system of equations up here. Now, there's going to be 3 equations and 3 unknowns, 3 variables. So that means my brace here, I'm going to have to write 3 equations in here. I'm going to write it this way. Just follow with me. If I have 3 variables, I'm going to use x, y, and then z is the standard other variable we use. I'm going to write 3 equations right here. I'm going to start by writing the last equation for you. You'll see why in a minute. I'm going to say z is equal to 2. That's it. Okay? The next equation is going to say y plus z equals negative 10. And then the first equation is going to say 2x minus y minus z equals, now let me think for a second. I have to think about this. I believe this is going to be 20. Hold on a second. No. Yeah, I can do that. That'll work. Okay. When you look at that, 3 equations, right? You see 3 variables in here?
Yeah.
What we're trying to do is figure out what x, y, and z are to make this true, right? To make this true, we want to find the x, the y, and the z. You know what z is, yes. Now, before I actually go through and do this, we know that if it's 2 equations and 2 variables, we've got lines, right? Because each of those 2 equations was a line. So we had 2 lines. The question that you might be asking yourself is, what is this if we were to try and graph it? And the answer to that is you can't do it on a flat sheet of paper. If you have x, y, and z, you need 3-dimensional space. So you need 3D. And it turns out that if you graph this in 3-dimensional space, it's not a line in 3-dimensional space. Like, it's not like here's 3-dimensional space and here's a line. It's actually a plane, which is like a flat sheet of paper. Okay? So this equation right here represents a flat sheet of paper in 3-dimensional space. It might be tilted or twisted, but it's flat and it extends forever in every direction. A good example of a plane in this room is this wall, right? This wall is a plane. So is the floor. So is the ceiling. So when you talk about, we're looking for a solution here, what are the possibilities with 3 planes and where they hit each other? Okay, so let's think about the case that we're most interested in. This wall is a plane, right? This wall is a plane, and the roof is a plane. Where do they hit each other? The top corner of the room, right? That would be a single point. So we could have that 3 planes intersect at a single point. Now this next one's a little harder. Where's my little, there it is. This next one's a little harder. How about this plane right here, this plane, and this plane?
Wherever that that is right there.
What is that? Is that 1 point?
No, it's multiple.
It's a bunch of points, but they all lie on a what? On a
X,
Uh,
Y.
what is that edge of the room there? What geometric shape is that? That's not a point. If I put all these points here, all those points right there, is this point on there? No. Is this point?
No.
On the other side of the wall? No. Just on that edge, right? What is that geometrically? A line. Right? That's a line? That's a line? Y'all agree? So we could have two planes intersect at a single point. We could have two planes intersect at a single line. How about this plane, the floor, and the ceiling? Where do they all hit each other? The floor and the ceiling don't, do they?
They're
So
parallel.
it's one.
So there's no solution. Now, where they all three hit. All three at the same time. See, if this plane right here hits the ground down there, right, in a line, but that plane doesn't hit it. So there's no answer to where all three hit. Got it?
No, all three of them are on that plane.
So what if they're all on top of each other, same plane? Then we have an infinite number of solutions, right?
Yes.
So with lines we had three things, right? We had hits at a point, they don't hit, or they're the same line. With planes we have some more scenarios. We have a point, they can hit at a point, they can hit at a line, they can hit everywhere, right? Or they can not hit at all. If there's no answer, excuse me, if there's no answer, then it's called inconsistent. We're most interested in the problems that I will give you are going to be where we have a single point as a solution. That's the geometry of what's happening. Now let's actually go through and do this. So before I sidetracked you on that thought, I said we want to find x, y, and z that make this true. And someone said, we know what z is, don't we? If I know what z is,
You also know what Y is.
then I can come up into the second equation and I can figure out what y is, right? So look at this. If I go to my second equation right now and write down y plus z is equal to negative 10 and replace the z with 2 and move it over, I know y is equal to negative 12, right? So now I know what y is.
Then plug it in back.
And z. And then now if I go to the first equation, I know that I can write 2x minus y minus z equals 20, which means that 2x minus y, what's minus y? Minus negative 12, so plus 12. Minus z, but z was positive 2, so minus 2, yeah. And that must equal 20, right? And you can solve for x. So 2x plus 10 is 20. You with me? Right here, this one becomes 2x plus 10 equals 20. Subtract 10 from both sides, 2x equals 10. And divide by 2, you get 5. So this would actually be the point 5, negative 12, 2. And the order matters. Just like x, y mattered, x before y, this has to be x, y, then z. So these three planes hit each other at a single point. Are we good?
I have a feeling it's going to be
Yeah, we start with this because this is kind of the motivation.
Proof of concept.
Yeah, if we can get our equations to look like this, it's easy, right? From here, it's easy. The problem is where we're going to start is not here. This is what we're going to try and get to. Once we're here, we are doing our back substitution. We're taking our z, going back up to get y. Once we know y, we take y and z and go back up and get x. So this is going to be kind of like where we want to get, right? So let's start with a fresh problem. And before I actually do it, I want you to notice something. Notice in the second equation, you were missing x, right? And in the third equation, you were missing x and y.
It's essentially the same as saying like 0x or 0.
That's right. This is like 0x plus 0y, right? Exactly. That's what this is. But I want you to see that we almost have this thing, it's almost like this little like triangle in here, right? We've almost like triangulated the equations so that one of them only has one variable, the other one has two, the last one up here has three. Our goal will be to get it to this. All right? You do remember some of this? Yes?
Is
Uh-huh.
this thing that we use matrices on?
12.2 is called matrices.
Okay, 'cause I don't remember.
Yep.
I just remember that calc looked like that.
Yep, that's exactly what it is.
College algebra.
Yep.
We taught you something.
Good, good. It's in there, right? You know, there is the difference, you know, in like oh wait, college algebra? You took 13, 14? Okay. Yeah, they don't cover this in 13, 14 anymore.
Really?
When did you do it?
Oh,
No?
no, like when I was in high school.
Oh, so algebra in high school.
Yeah.
Okay, you said
It's
college.
college algebra. Yeah.
Oh, it was? Okay, good. Yeah, the difference there, the only difference is that y'all have a lot of time to cover it. We like kind of are going to do it in like 2 days, you know, that sort of thing. Okay, let's look at this. 2x plus, now before I write it down, I just want to double check something here. 12.1. Can y'all believe we only have 2 more weeks and then finals?
Yes.
You're so ready?
I'm not ready.
You're not ready? Why?
How,
I don't want to
just, I know this is a random question, but how many problems do you only place on the final?
And I looked it up on Break My Teacher. Just,
He's gonna only
What?
put like
I know
two
we
out
have
there
3
and
hours
over
to do
everything.
it. Yeah, I know we have 3 hours to do it. So how many problems?
I'm guessing it's going to be around 20 to 30. Is
Okay.
that okay?
Well, I knew we had 3 hours, so I was just like, with your problems, I was like, well, hopefully he doesn't give us like 50 or something.
Oh, no, 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 no. I wouldn't do that. It'd be like 48. 48 or 49. I wouldn't do 50.
so I looked up the professors.
Mm-hmm.
And it was like in vet something.
Mm-hmm.
And I looked up on Break
Just
My
maybe
Teacher.
just have it the
Mhm.
same questions.
And no, she just seems to be.
Yeah, that would be awesome. Well,
We did just look at it, and now we just drop out.
No. All right, well, I was going to give you one that didn't give you fractions, ugly fractions. But I guess we'll start with one where you're going to get fractions. So 2x plus y minus 3z
and one of the
negative 2x plus 2y plus z. I forgot to put equals up here. Equals 0 equals negative 7. And then this last one, 3x minus 4y minus 3z equals 7. There we go. We have a system of linear equations. We have 3 equations and 3 unknowns. 3 variables. I keep on saying unknowns, I'm sorry. Variables or unknowns, those are the same thing. What's that?
Do we do the elimination?
Yeah, so this is where substitution, I told you, is a nice method, but it's not as powerful. Substitution, if you tried it on this problem, would be very difficult. Because you can't solve, you could solve for one variable in any of these, but then when you plug it into the other one, you're still going to have 2 variables that you don't know. So elimination's the preferred method.
So you have to get all the x's to cancel.
Yeah, so let's start with this. I know that I need that to go away, that to go away, and that to go away, right? Eventually I want those gone, don't I? Those are like the spaces that, or the places where I need to create zeros. So let's start by just focusing on the first equation and the second equation, just those 2. Yes?
Can we move like the top equation to the bottom?
You are free to move equations around, yes. But I am not going to do that. I'm just going to attack it the way it's presented. But yes, that is a legal move.
Well, the first one is pretty much done.
Yeah, look, if we want to kill off the x's here, right?
You don't need to do anything.
I don't need to do anything. I just add straight down. So when I add those 2 down, what do I get? I'm going to write this on the side. Just what would I get? 3y minus 2z equals negative 7. That's what I would do? That's what I would get? If I just add, I'm ignoring this one.
Okay.
Just working with the first 2. That's gone. 3y, negative 2z, negative 7. Now, the question becomes, what can we do with this? I mean, we know that that's true, right? Here's what you're allowed to do. And there's a whole bunch of different things that you're allowed to do. All right? One of them is, and pay attention to what I'm saying, when you have a system of linear equations, you can multiply any equation by any number. We kind of already knew that, right? You are also allowed to add any two equations together, which we've done already. Bless you. That's such a good sneeze. Once you add them together, okay, this is the one that doesn't seem as normal or natural. When you add two equations together, you are allowed to take that answer and replace either of the two equations that you started with that answer. All right? You're allowed to do that. Now you might be asking, why are you allowed to do that? Did I show you the story about the kid who was in the class and the teacher told them to add up the numbers? Remember that? Yeah. His last name was Gauss. This method we're using is actually technically called Gaussian elimination. It's a method that was developed by Gauss, and it's already been proven. He proved it all that you can do this. It's allowed. So all you need to know as a college algebra student is that you're free to do it. All right? Not necessarily like why it works. I hate to say that in classes, but it's an entire method called Gaussian elimination. And all these things I'm telling you you can do are valid. So I'm allowed to take this answer and replace either one. Now I'm going to do the middle because I want that to be gone, and if I replace it with this, it is gone, right? So what I do now, and this is kind of where this gets a little tedious, is that you need to get in the habit of just rewriting the entire system of equations again. Yes?
So let's say that the 2x and the negative 2x didn't go along. I mean,
Okay, so yeah, let me write this and then I'll answer your question. 3y minus 2z equals negative 7. And then we still have down here 3x minus 4y minus 3z equals 7. The question was posed, what would happen if these hadn't canceled, right? Then you would have just multiplied these by whatever number to make them cancel.
so it would have divided and bottom.
You would not mess with this one. Not yet. But in fact, that's what I'm going to do now, right? Because I've created one space. I've created one space that I wanted. Now I need to make two more spaces. So this one's good, right? Now I'm going to make a space. I'm going to work on this one next. So I go down like a column and take care of all the x's first. So I'm allowed to start my entire thinking over. I want this x to go away. This is the only equation I have to work with that has x's now. So I need to make this 2x and 3x go away. Multiply 3 up here and negative 2 down here. That way they'll be opposite in sign. And I'm going to rewrite the entire system. Please get into the habit. I know it's going to make your hand hurt and you don't like writing, but get into the habit of rewriting the entire system, because when I'm grading these and I'm trying to find out where you made the mistake, if you don't have all your work, then it's just going to be wrong. As opposed to, oh, I see that you did 3 and 2 and messed up there or something, you know? Then I don't take off as much. Distribute the 3 through to all terms on both sides of the equation. So what does my new top equation become?
6x plus 3y minus 9z equals 0.
Everyone agree? Second equation, I'm not even messing with yet, right? I'm just going to let that one come along for the ride. And then my last equation, negative 6x plus 8y plus 6z equals negative 14. Now, using Gaussian elimination, I can add any two rows together. The top one and the bottom one, right? The first row and the second row. That answer, which would be what? Place that on the side over here. This one and this one, ignoring the second one this time.